Today we're going to be looking at radioactive decay and how it relates to something called half-life. On Monday and Tuesday we're going to be looking at fission and fusion. Well, I want to try to get it done on Monday. Tuesday and Wednesday we'll be looking at modern physics. We're going to study modern physics in 2 days, which tells you that we're not really going to learn an awful lot of details about that. It's going to be a general overview. If all goes according to plan, that second lesson on modern physics, which is on Wednesday, is not really even necessarily a full lesson. So we're going to be reviewing a lot for this exam that we write when we get back. If we didn't have a break, you'd be writing it the day after next Friday, but that's a Monday following a 2-week break. So we're going to have like 3 days of review. Today we're looking at radioactive decay and half-life. If you've taken or are in Math 30 right now, you already have kind of a leg up on everybody else. You understand what radioactive decay and half-life is about. We're going to be interpreting half-life graphs for radioactive decay and doing half-life calculations. So if I have a sample, we talked about this before, and a little bit later in class I might get out the radioactive sources again to demonstrate something to you. We'll see. We may not do that till Monday. But I've already talked about this, that we take that polonium-210 and I put it in front of the Geiger counter, and the Geiger counter goes crazy picking up all these alpha particles. And then a half hour later I put it in front of the Geiger counter again and it's still ticking. And what that means is that the polonium-210 nuclei are not all in one organized burst of energy decaying all at once. Some of them decayed a year ago, some of them decayed yesterday, some of them will decay a year from now. And the question is, what determines why some of them decay and some of them don't when they decay? And the answer is statistics. I know this is hard to wrap your head around because you think science is some kind of exact science. You think that there's formulas and accurate predictions are made, that you don't realize that sometimes there are physical laws which are very accurate when it comes to large populations of things, but not accurate when it comes to predicting any particular individual. I'll give you an example, and it's not science, I guess maybe it is, but it's more math. That if I have a coin and I flip a coin and I say, does it land heads or tails? You can't answer that question. You really can't. It landed tails, okay? But if I pick up that coin again and I toss it again, just because it landed tails doesn't mean you know whether it's going to land heads or tails. This time it landed heads. It's not going to alternate back and forth, right? So if I were to toss this coin 10 times, somebody who doesn't understand statistics would believe it's going to land heads 5 times and tails 5 times. Because the probability of it landing either heads or tails is 1/2. But it won't. Is it possible that it lands heads 10 times? Yes. I'm assuming it's a fair coin, by the way. Is it possible that it only lands heads once? Yes. So if I toss this coin 10 times, the likelihood of getting 50% heads and 50% tails is actually quite small. But if I tossed 1 million coins all at once, I guarantee you the percentage that landed heads would be 50.000 something, and the percent that landed tails would be 49.9999 something. They would be very, very close to 50% each. And the larger the population is, the more accurately that prediction is, the more accurate it is. So we cannot predict, if I look at a nucleus of polonium-210, we cannot predict whether that nucleus is going to decay or not. It's a magnetic coin, in case you're wondering. It's a magnet. We cannot predict whether that particular nucleus will decay, but we can say with certainty that it has a 50% chance of decaying. And that's exactly what's going on with radioactive decay. It's very, very similar to the probability of tossing a coin. The period of time that we say the nucleus has a 50-50 shot of decaying or not, that length of time over which that probability is 1/2 is called the half-life. In other words, you know what the half-life is? It's a single coin toss of all of the coins. Except, and you understand analogies are never perfect, the atoms don't hang around, the nuclei don't hang around for a half-life, and then all of a sudden half of them decay. Okay? They're always decaying over time, but on average, half of them decay in that half-life. So, if during one half-life, the probability of each nucleus decaying is 1/2, or if you want to use 50%, I think in 30-2 you talk about percent with probability, then you would expect half of them to decay during that time. And that means this. When you read the half-life of carbon-14 is 5,760 years, that means every 5,760 years, half of the carbon-14 that was there is no longer there. What is there in its place? Whatever carbon-14 decays into. All right, we have a bit of a warm-up here. The half-life of carbon-14, I was wrong, is 5,730 years, not 5,760 years. So I've got a chart here. The number of half-lives elapsed is 0, 1, 2, 3, 4, etc. And the age, I hope you understand with a bit of thought where these numbers of years are coming from. Because you're told up top that the half-life is 5,730 years. So one half-life is 5,730. 2 half-lives is twice that. Apparently 2 times 5,730 is that number. 3 times it is the next number, etc. We're not going to worry about plotting those years, but I want you to understand that they are years. So what percent of carbon-14 is remaining in the sample relative to the amount of carbon-14 it has at the beginning? Well, I'm telling you it starts at 100%. It may be that the sample that contains carbon-14 is maybe only a very, very tiny part of it is carbon-14. It's not pure carbon-14, but there's a certain amount of carbon-14 in that sample. And how many of you have heard of carbon-14 radioactive dating, where you date the age of samples with carbon-14? We're going to talk about that in a bit. After 5,730 years, the percentage that's going to be left will be 50%. For you people in Math 30 right now, what we're talking about here is an exponential decay with the base of 0.5 because it's being multiplied by 0.5 on regular intervals. After an additional period of time, that's the half-life, 25% decays. Then what I mean by that is we're only going to have 25% left. We went from 50 to 25, so 25% of the original sample is now wiped out, and we're only left with 25. And then it goes down to 12.5 and 6.25, and on it goes. Once again, we're not saying it's pure carbon-14, and that becomes important for later. So compare the amount of material that decays as time goes on. This is an interesting thing. And I don't maybe need to talk about it in Physics 30, but many of you will take calculus, and this is the basis for any type of natural growth or decay. When you take a look at the chart, in going from 0 half-lives to 1, we lose 50% of the material. Let's say, it's not really possible, but let's say we start off with 100 grams of pure carbon-14. I mean, we might have 100 grams, but it wouldn't be pure. It would be mixed in with some other stuff. What that means is from 0 to 1, we have lost 50 grams, right? 50 grams has decayed. But then when we look at from 1 half-life to 2 half-lives, we've only lost 25 grams, right? So what's happening as time goes on is less is decaying, which is maybe a little troubling for some people until we really think about it. So the answer to this question is the following. As time elapses, less material decays. And I never used to include this question. Do you even have that question? So I took it out, but I'm going to leave it in and we can just talk about it. I never used to have the question, then I put it in, and apparently this semester I decided to take it out. But a student asked me one time, when we were talking about this, she pointed out that we did have less decaying as time went on. And she asked a question which is not a silly question, it's a great question. How does the carbon-14 know that less should decay later on? It's a great question. Like, how does the carbon-14 know that down here, less of it has to decay? The answer is it doesn't know. The best answer, you could say, well, because it's always half of what's left, but that's not a real understanding. The better understanding is this. If there's less there to decay, then there is less there that will decay. Right? Forget about the 1/2 thing. There's 100 grams that has a chance of decaying, so you're going to get a lot of decay. Down here, when we're down to 6.25 grams, well, there's very little stuff that can decay, so there will be very little decays that happen. It's what I would explain in Math 31 in terms of exponential growth. If we looked at a honeybee population in a hive, and it's growing exponentially, what that student's question is the same as is, how do the bees know that they should increase their rate of growth later on? And the answer is, there's more bees that can reproduce to make more bees later on than there were bees at the beginning. So as the population of bees goes up, the number of bee babies goes up because there's more bees to have babies. As the number of nuclei goes down, there's less nuclei that can decay, so fewer will decay. All right. Let's plot a graph here. So what do we start off with? We start off with 100%. Then it's down to 50 after 1 half-life. Down to 25 after 2. Down to 12.5 after 3. I don't know that I really want to go to 5. 6.25, I guess I can. And I believe for 5 it was 3.125. So I'm going to address my Math 30 students right now. There's an asymptote here, right? Mathematically. And in Math 30 we would say, wow, the graph never reaches that 0 point, which is why there's an asymptote. Don't draw this in. Even if you've only taken Math 20, you should understand the concept of an asymptote. Don't draw this in. In math, we would say there's an asymptote there. The function has an asymptote. There is no asymptote. This will reach 0. It has to reach 0. When you stop and think about what's going on, forget about percents. Sooner or later, you'll have maybe 14 nuclei that have yet to decay. So we wait 5,730 years. And maybe 7 have decayed, half of them. Maybe 1 has decayed. Maybe none have decayed. Maybe they've all decayed. But sooner or later, if you wait long enough, you'll be down to that 1 nucleus. And sooner or later, it will decay. So this is going to reach 0. What the graph looks like is the following. Do your best to draw a curve. I'm not great at drawing curves on vertical surfaces. That's not bad. So it looks something like that. This is different than some of the relations or relationships we've looked at before because there is a y-intercept. It starts somewhere. We have looked at, I don't want to get too far away from what we're talking about here, but we have looked at things like the following. The electric force between two charged objects as a function of the distance, and it looks like this. And there are asymptotes here. But this graph doesn't have a y-intercept. So be careful. Well, mathematically, and you Math 30 people will understand why this is the case. What's happening is you have a base of 0.5 that the population of nuclei is being multiplied by regularly. Unfortunately, in math, we have a perfectly reasonable formula. I think this makes a lot of sense. And if you don't know what I'm talking about because you're not in Math 30, if you don't know what I'm talking about and you are in Math 30, you better start studying for your diploma exam, okay? But if you're not in Math 30, don't worry about it. I love this, but unfortunately, this is the formula we use in physics. And somebody has decided to label everything with n. On our graph, the vertical axis is n, and the horizontal axis is little n. It's not time. So you Math 30 people, we have in math this beautiful formula which relates the population to the time, to the days, or to the years, or to the seconds, or to the months. This formula relates the quantity of the population to how many half-lives, not to the elapsed time. So n is the number of half-lives. N0 is the original population. And capital N and capital N0 could be percent. So N0 could be 100%, and N is a percent that's changing, the percent later. N and N0 could be grams. Okay, so N0 might be 13 milligrams, and then N is showing what's happening to that. Or it could be something called decay. Oh, sorry, it could be something called activity. And activity is how many decays per second. So imagine that radioactive isotope of polonium-210 or whatever you want, and I put it on the Geiger counter, and it's clicking away, right? And if we counted, and there's a meter you can read it, if we counted 1,000 ticks per second, that means at that point in time, there are 1,000 decays per second. But if I leave that polonium for a few months, remember the half-life of polonium is very short. Armand had asked about that. It's only like 138 days. If I leave that for a few months and then I bring it back, I will not get 1,000 decays per second because there will be less that's decaying because there's less remaining to decay. So it could be activity. Activity is the number of nuclei decaying per second. And again, it makes sense that if there are fewer there to decay, there are fewer there that will decay. So that exponent on this formula, and I usually just write 0.5 here, and I'm pretty sure you're okay with that, is the number of half-lives. And this, which is not on your formula sheet, is the connection between number of half-lives, actual elapsed time, and the half-life. So we use H as the half-life here. In Math 30, we would use P as the half-life. You with me on that? That it's T over P and P is the half-life? Okay. So let's do some problems. In a radioactive sample of polonium-210 with a half-life of 138 days, if an original mass was 40 milligrams, how much polonium-210 will remain after 1 year? So this is a simple question, really. We have n equals n0 times 0.5 to the n. I'm not a fan of putting up here for n T over H. And I'm not really that big of a fan, actually, of memorizing this formula that's in black. I mean, to me, it makes sense that if the half-life is 138 days, and we're talking about 1 year, I have to take 138 and divide it into 1 year to see how many half-lives it is. Before anybody asks, do you need to go 365.25? No. You can just go with 365. So how many half-lives is that? Well, somewhere between 2 and 3, it looks like. 2.645 half-lives. You know, what are the units of this? They are half-lives. The initial quantity is 40 milligrams. So the quantity remaining after that period of time, I make a big deal of it in math, so I have a lot of math students here. I'll make a big deal of it here. These are your variables. The other stuff are parameters. They're numbers that just define the particular situation. So we run this through the calculator, that's all. 40 times 0.5 raised to my answer, about 6.4 milligrams. Now, the next question is going to lead into something which I think is important. It's not that we had a block of 40 milligrams of this stuff and you come back a year later and there's just physically that much less material. It's probably still 40 milligrams, close to 40 milligrams. It's just that only of that 40 milligrams, only 6.4 is still polonium-210. Right? The radioactive decay doesn't involve an isotope disappearing. It involves an isotope changing. After 1 year, what percentage of the original sample will be daughter material? Well, this is a little iffy. It's not perfect. But what we're saying is that the amount of parent material, the amount of polonium-210 that's still left is 6.4 milligrams. That must mean that the rest of it is the daughter material, which is 33.6 milligrams. How's my subtraction? How many of you see an error in my logic that's saying the remaining mass is that? Or the mass of the daughter material is that? Let me write down daughter first. Alex, do you know?
It's decaying that loses mass.
Right. Well, it's losing mass because of radioactive decay, loss of mass to energy, but also that's not including all the alpha particles that went for a ride, right? There's a whole stream of alpha particles that left. Bottom line, though, is we can answer the question, even though this is not precise, I'm giving it to you to try to impress on you that it isn't that the mass just goes away. There's still that other 33 whatever grams of the daughter present. So 40 minus this divided by 40 times 100, about 84% of the original sample will now be the daughter material. What is the daughter material? Well, that's a piece of cake. Polonium-210, figure it out with alpha decay. What do we have? 210. Polonium is 84. 42 is alpha. I mean, right away, you don't even need to finish this. You can see what it's going to be. It's going to be 82 on the bottom, which is lead. 206. So the daughter material is lead-206. About a year later, 84% of the sample will be lead-206, and the other 16% of the sample will be polonium. I hope you understand that if this represents the block of material to begin with, there will not be some kind of line here where everything to the left of the line is the 16% that hasn't decayed, and everything to the right is the stuff that has decayed. I hope you understand that the 16% left, I'm not going to stand here like an idiot until I get 16% filled in. The 16% left is going to be scattered throughout the thing. Okay? So now I want to talk about radiocarbon dating. And we could analyze many of these things we've talked about and I'm going to talk about in detail, but my hope is by talking about them in general to you, if you do see details on an exam, you know what to do. It turns out in the upper atmosphere there are different isotopes of carbon in the carbon dioxide. And it turns out that some of that carbon is carbon-14, which decays into a different carbon or a different nuclei, I'll say, nucleus. But it also turns out that our upper atmosphere absorbs UV radiation, and the result is you get a nice equilibrium of carbon. There's carbon-14 that's decaying and carbon-14 that's continually being replenished through a cycle. And anytime I eat something, I ingest carbon. And some of that carbon is exhaled through carbon dioxide. Much of that carbon turns into muscle mass or other tissue, especially as you're growing. But I have radioactive carbon in me right now. And it's decaying. But because I'm continually eating and exchanging carbon with the atmosphere, the amount of carbon-14 in me, as long as I'm still breathing, stays the same. It's decaying, but it's being replenished at the same rate. And it turns out that in a living, breathing organism, the total amount of carbon-14 decay is about 0.23 decays per second. So if you had a sensitive enough Geiger counter that could only detect carbon-14 decays, and you could somehow have a big Geiger-Mueller tube that would just be pointed right at my whole body, it would be ticking about 1/4 of a time every second. In other words, 4 times, once every 4 seconds. Okay? As soon as a living organism dies, that exchange ends. So as soon as, maybe we'll look at it this way. If you have a living organism, if you have a living organism, this is what the graph looks like. As soon as you have a dead organism, it looks like that. But what that means is I can take a Geiger counter, I find a piece of leather, which is from a cattle or a cow or something, and I can take that Geiger counter and I can measure the activity of that, and I can use physics to find out how long ago it died. This is what radioactive carbon, radiocarbon dating does. So this is data from an actual discovery. Poor guy, they found this guy, he was wearing these clothes, very primitive type of clothes, but shoes and sandals he had made. He had a spear, he had hunting tools, and he was wedged between 2 rock formations in a mountain. The poor guy was out hunting for food, and he slipped, and he got stuck in there, and he died there. And this was discovered, I think, maybe about 30 years ago in Europe, and then they did some analysis at the U of A. They took a piece of the leather sample, and they measured the decay rate to be 0.0018 becquerel, which tells you that they didn't sample him, they sampled the piece of leather from a sandal he was wearing, but the leather was from an animal, right? So there's the animal, carbon-14 going along great. I saw this from last semester, so I thought I would keep it. Let's slaughter the animal, get some food, get some clothing. Right now is when the carbon-14 starts going down. Because the cow is no longer exchanging with the environment. And that's what we need to find. The half-life of carbon-14 is 5730 years. The initial activity is 0.23 becquerel. The activity of the sample at a later point in time is 0.0018. We're going to use this formula to find out n, little n. Now, those of you that are really good at exponential functions and stuff from Math 30, you could go further and you could put t over p up there or t over h up there. But I'm just going to speak to the Physics 30 students here. So I put in 0.0018. I put in 0.23. And is there anybody right now, and I know there are, but I want to know who they are, who has either not taken a grade 12 math or is not in grade 12 math right now? So what I'm asking is, who here is taking grade 12 math next semester? Okay, so you don't know how to solve this officially for n. The best you can do, and then I will show everybody, is first of all divide both sides by 0.23. To get 0.0078, we'll carry all the decimals, equals 0.5 to the n. I hope that those of you that are in my Math 30 class right now look at that and go, that's a piece of cake to find n. Okay. I'll go over that in a second. Well, maybe not. Okay. So how is it you can solve this now? Well, one of the things you can do is solve it graphically. I mean, we could graph 0.5 raised to the x and 0.0078 2608. Now keep in mind, 7, that y equals 0.007 means it's a horizontal line down at 0.007. We do know from this class, not just from Math 30, that this graph will go down. We're looking for a point of intersection here between y equals 0.0078 and 0.5 to the n. So when I do this, I would set up my window, and I want to get rid of this little dot. Don't worry about what it is. I would set up my window to go vertically from 0 to 0.01, which is a little bit more than 0.007. I would also use a bit of common sense and say, if I divide 0.3 by 2, I get about 0.1, 0.23 by 2. And if I divide by 2 again, I get about 0.05. I'm thinking n will be 2 or 3 half-lives. So a little bit of common sense goes a long way here. Let's go up to 4. Might have to go a little more. Let's go up to 6. Why am I not seeing the other graph? You know, I think maybe I'm just not seeing the other graph because I'm looking at such a tiny, tiny layer of the graph. Sorry, I want to sort this out. This is bothering me a little bit. I'm going to come back to that. Let me show you how to, Alex, have you had time to figure out how to solve it with logarithms? Don't remember?
I remember, but I think is it logarithm of 0.05 over logarithm of that? Or is it
Well, you will know if you follow the rule. What do we do, Armand? Do you know?
Logarithmic of 0.0078 divided by logarithmic of 0.5.
Why? That's right, but why? Why? What's going on here? Do you remember, Sasha?
I think so, but I don't know why.
Okay. What do you do to both sides? Take the log of both sides. Okay. So, and this is something that, and I'll come back to my graphing calculator in a second. Take the log of both sides, and if you are not in Math 30 right now and haven't taken Math 30, just think of log as being some magical thing that makes nice things happen. Okay. Don't worry about what it is, because that's a whole unit. When you take the log of something like 0.5 to the end, it allows you to move that exponent out in front. So this becomes n log 0.5 equals log 0.0078. So we have to take log of 0.0078 divided by log of 0.5. And that actually is a calculator function. It's right here, log. Again, don't worry about what it is. If you haven't taken logarithms, it's a 2-week unit. Log of our answer divided by log of 0.5. So little n, oh, you know, I just didn't go far enough, I guess. I don't know. My confidence level today is, I didn't think it was that big looking at the numbers. Oh, there it is. I just didn't go far enough. My math analogy, I didn't walk down the road far enough to see if it would bear fruit. And you could find the solution by finding the intersection point here. So you get 6.9984 there. If you do it using the logarithm thing that you Math 30 people should remember, even though you might not, you get that. If you do it using the logarithm thing and you people that are not in Math 30, maybe you're better off. You just remember how to do it. So that's not the answer to the question. That's the number of half-lives. We still have to multiply by how much each half-life is in order to get the number of years. 5730? Thank you. So this is the number of half-lives. If we multiply that by 5730, this poor fellow was going for a walk, trying to find some food for his family 40,000 years ago. Okay. Any questions with that example? Now, I have a different question for you, and then we're done. Can carbon-14 dating be used to determine the age of fossilized dinosaur bones? And there's one reason why I want to discuss this briefly, okay? And we'll get to that reason in a second. Well, the answer is no, okay? I'll tell you that right now, no. You understand that, you know, the show The Flintstones is fiction. I mean, I know it's fiction because it's cartoon, but primitive people did not live at the same time in history or in terms of, well, history of the earth as the dinosaurs. Human beings had not yet evolved to be human beings, not even primitive human beings. And just with a general knowledge here, and as a boy growing up, I studied dinosaurs. I was really into that. I know they existed millions and millions of years ago. So why is it carbon-14 dating would not be successful in trying to find the age of fossilized dinosaur bones? Even assuming that the dinosaurs were breathing the same atmosphere that we're breathing now, which there's science in figuring out why that's not the case and what it would be. But even assuming it was, what's the problem here?
It's been so long that there is no carbon-14.
It's been so long that there is no carbon-14. How many half-lives do you suppose it takes for the carbon-14 to, or anything, to go away? Like, do you remember Armand had asked, what's the time on those radioactive samples? And I picked on the polonium with 138 days, and then I showed you I have a whole container full of old polonium samples that are dead. Because every 138 days I lose half of it. Well, it turns out I generally say 10 half-lives, you don't have much left. Okay. I mean, can you toss a coin 10 times and get heads 10 times in a row? It's possible. Is it likely? Not very likely. If you were to take a stadium full of 60,000 people and they all had a coin and they all stood up and they tossed the coin and they looked at it in their hand, and if it's heads, they sit down. Half of them are going to sit down after one toss, right? After another toss, half of them are going to sit down. Sooner or later, you'll be down to 2 or 3 very quickly, and it won't take much more than 8 or 9 tosses. Is it possible that you might still be there after 20 tosses? Incredibly unlikely. So I say 10 half-lives, there's nothing left. So I'm just going to say no, there's no carbon-14 remaining. Or there, I mean, is it possible that, and I hope you understand, fossilized dinosaur bones are more than 10 half-lives of carbon-14. But is it possible that after 10 half-lives there are some carbon-14 left? Not many. So it's very hard to detect. The percentage remaining, if I take 100% and I multiply by 0.5 raised to the 10, this is going to give me the percentage of a radioactive material left after 10 half-lives, which, by the way, is only about 57,000 years for carbon-14. Not bad. 0.1%. That's already a percent. I'm not going to multiply it by 100. But there's less than 0.1% there. Very hard to detect. If I were to go to 20, forget about it. I mean, there's nothing there in terms of a percentage to detect. So the problems you're working on here deal with that formula, basically.